This next example, integration by parts, section 7.2. This is video number 5 for this section. We're looking at the integral of e to the 2x sine of x. Now, in all the previous examples we were playing with, there was an algebraic function to start with. So the one thing that you're going to want to make sure you remember is with the algebraic functions, the derivative of those always made it more simple. Well, the problem here is that the integrals of both of these functions are just going to cycle, and the derivatives of both of these functions are just going to cycle in some form or another. So that means that we're going to have to try and figure out a way that's going to make this work. Now, if we were lecturing this in class, I would definitely go through messing this problem up a few times, attempting to do it in multiple different ways. But I think for this particular video, I'm going to focus on what I think is the simplest way to do this problem. And again, you're going to have to practice these particular examples. They come up relatively unfortunate, and it's a matter of deciding for you what is easier and what is more complicated. So I have to let u be one of these functions and dv be the other one. And again, don't forget your dv always has that dx attached to it. Now, if I were to let dv be e to the 2x, that means that for me to integrate e to the 2x, I'm going to have to do a u substitution inside of my integration by parts method. Again, e to the 2x, I'd have to do a u sub on this 2x if I'm just trying to integrate that, which would then force me to have to divide by 2 somewhere in the problem. Again, if you're struggling with that particular concept, come see me during office hours. But in terms of this example, if I let u be e to the 2x, and my dv be sine of x, then this integral is not nearly as problematic. And again, remember, if I'm integrate sine goes backwards, I'm going to end up with a negative. So yeah, sure, it does make this problem more complicated with a negative cosine of x. However, the derivative of e to the 2x is definitely a lot more easier to deal with than taking the integral of e to the 2x. So the derivative is going to be e to the 2x times the derivative of the inside, which is 2. So 2e to the 2x, and then don't forget your dx attached to the end. So now I've selected a u and I've selected the dv. Again, it doesn't seem entirely arbitrary of which one I've selected, but to be honest, it really is. You may let sine be here and you may let e to the 2x be here, and you will still end up with more or less the exact same answer. And when I say the exact same answer, it's like having a dollar in one hand and 4 quarters in the other. They might not look the same, but you will have the same, differing by no more than a constant. So, in this problem right here, if I do this work accurately, I end up with e to the 2x sine of dx becomes, again, uv, so a negative e to the 2x cosine of x. And again, I like my negative to be up front, but I like my e to the 2x being first and my cosine there. And then minus the integral of v du. So I'm going to end up with a negative, again, I'm going to put the 2e to the 2x first, the cosine next, and the dx last. Now again, where are all these pieces coming from? Remember, this is the integral of v, negative cosine, du, 2e to the 2x, 2e to the 2x, and then don't forget your dx tacked down to the end. Now, but you might be looking at this saying, well, wait a second. This was the original integral. This is no more simple than this. And you'd be right. This is not more simple than this. But bear with me, we still have to be able to integrate this. I'm not going to give you a problem that you can't integrate by hand. I'm going to pull this negative out. I'm going to pull this 2 out as well. Yeah, I'm going to pull that 2 out as well. So plus 2, integral of e to the 2x, cosine of x dx. So now we're at a problem here. We're more or less back at the same integral, but it's not the exact same integral. So what we could do, and again, this is probably what I would attempt to do in class, is I'd say, well, let's try letting u equal cosine and dv be e to the 2x. But if you recall in a previous video, I said if we've let u be one of the functions and dv be the other, and then we have to do the integration by parts again, never swap the types of functions. So up here, I let u equal the exponential. If I've got to use integration by parts again down here, I'm going to let u be that exponential function all over again. Okay, so again, one more time, do not swap the functions. You'll do nothing more than backtrack to this original integral with nothing else. Okay, you're simply going to undo what you did. Now, I'm going to go ahead and pick my dv as being the other piece, that cosine of x dx. And therefore, I'm going to have my du be the same exact du as I had before, 2e to the 2x dx. And my dv ends up going to transition to v as, again, the integral of cosine transitions to sine of x. So it's not the exact same transition here as it is here, but hopefully this will still work out for us. And again, keep in mind, I'm not going to give you a problem you can't do. So yes, it looks like we're doing nothing but backtracking, but that's not actually what's happening. Don't forget that there's this 2 here as well that we didn't have before. So I'm going to go ahead and carry all the pieces down that I can. This is equal to the negative e to the 2x cosine of x plus 2, and then this whole integral is going to transition based on the uv integral of v du. So I'm going to go ahead and have my e to the 2x sine of x. That's my u times v. Again, this integral, I'm going to go throw it in brackets so that you see where it's coming from. These brackets are becoming these brackets down here. So I'm going to have uv minus the integral of v sine of x du. So 2 e to the 2x sine of x dx. And again, where that comes from is the sine comes from v, the 2e to the 2x dx comes from your du. Okay, and now you're looking at this going, well, wait a second. We didn't really get anywhere. This right here is almost the exact same as this with an extra 2 inside. Well, bear with me. I'm going to go ahead and rewrite the entire problem from start to finish. And what I mean by that is the original problem we had was the integral of e to the 2x sine of x dx. That was the original integral. We know it is equal to this entire thing here, which I'm going to rewrite. I'm going to simplify some things, distribute some things out. So it's equal to a negative e to the 2x cosine of x plus, distribute the 2 to this term, and then make sure you distribute to that term as well. So plus 2 e to the 2x sine of x. And then distribute the 2 to this one here, so a negative, there's no negatives inside here, 2 here, 2 here. So that becomes 4. And then the integral of e to the 2x sine of x dx. So we're looking at this singular line of information, and what was the goal of this problem one more time? It was to evaluate, in the start, evaluate this integral. So if I could get this integral all by itself equal to something without an integral in it, we're done. Well, hopefully by this point you're looking at this thing going, well, I have no idea what's going on, or you have an idea of saying, well, wait a second, this is the integral we started with. Yes, it's all by itself, but it's equal to something that has an integral with it. But the hopeful part is that you'll notice that this integral is the exact same as this integral. It's got a 4 with it, but it is the exact same integral. So what I'm going to do is way back up here, I'm going to say let this whole integral equal to a. I'm going to let it equal to a so that down here I can visualize this as a equals to negative e to the 2x cosine of x plus 2e to the 2x sine of x minus 4a. Notice, by doing so, there is no more integrals in this problem. I will combine like terms by adding the 4a over, giving me 5a, or 5 of those integrals, equals to all of this information right here, negative e to the 2x cosine of x plus 2e to the 2x sine of x. Don't forget you have to tack on a plus c, and don't forget that you need this integral by itself. Since it's 5 of these integrals equals to all of this information, I'm going to cross out this 5 and say one of these integrals is equal to all of this stuff here divided by 5. Notice I didn't extend it to that c, because in theory the c will absorb that 5 and it won't be important anyways. So this is your final answer. Yes, you will see some examples like this, and this is arguably the worst example that you'll come across, is where you're going to have to apply integration by parts on a problem that has exponential and algebraic together, exponential and trigonometric together, and you do it once, and it doesn't change the difficulty of that second integral. And therefore you have to do it again in order to identify the exact same integral you started with and treat it like it's an algebra problem. Again, these examples come up more frequently than you'd like to admit. So now we have a couple of rules in terms of basics of how to integrate and what we're going to let u be and what we're going to let dv be. Again, the statement is u will normally simplify the expression. So pick whatever you can pick for u that will take the function and make it more simple, either algebraically or in transcendental functions, which is again what exponential and trigonometric functions are.